Okay. We are back in the saddle. All right. Where did we leave off last time? We were watching a video.
Yeah, I didn't quite finish.
Let's watch the video somewhere. That's the one we're on.
The free neutrons, and some of them hit other U-235 atoms, keeping the chain reaction going. But others of those slowed down neutrons hit U-238 atoms. And here's what happened. Remember, we said that U-238 wouldn't support a chain reaction. However, it will capture neutrons from U-235 fission and start a process which
So the neutron captured by U-238
converts
that
to
decays
U-238
to
first
become a proton and becomes neptunium. We ended up on this idea.
to neptunium,
And then another neutron inside of the nucleus decays and becomes a
then
proton
to
and
plutonium.
becomes plutonium.
And plutonium will fission in chain reaction.
And this is actually what most of the nuclear bombs that we have now are made of, because U-235 is actually very, very rare. But plutonium is easily made in a nuclear reactor from U-238, which is not rare at all. Uranium-238 is very plentiful.
And it's just more stable than 235, or why won't it work?
It is more stable, yep. It's also radioactive, but it's just more stable. In fact, when they were separating the U-235 from the U-238 to make the first bomb, they literally ended up with a mountain of U-238 left over. And the problem was that it's still radioactive, so it still gets really, really hot, and it still puts off radiation. And they found that they had to store it in small piles, essentially, so things didn't get too hot and things didn't get too radioactive. They had a real problem with figuring out what to do with it all. So they eventually started realizing what they could do with it to make plutonium, and they started making rods and things out of it. It's also very useful. Uranium-238, when you can actually excuse me. When you're using it to do certain things, as it decays, because it is radioactive, it actually can become another isotope of uranium. I don't remember which, but it's depleted uranium is what it's called, and it's still uranium still extremely dense. So uranium is about twice as dense as lead, so it's very, very dense, and it's also extremely refractory, as they call it, which means that energy just bounces off of it. All kinds of energy, including like gamma rays. Gamma rays, which have a tendency to be able to go through just about anything, do not like to go through uranium. And it refracts energy extremely well. And so what they started doing with it is making projectiles out of it for tanks and armor out of it for tanks. So tanks now have uranium armor on them and uranium projectiles to go through armor. Well, tanks in the United States anyway. So they have this incredible metal that is really good at absorbing and reflecting energy on the outside, and then they make their bullets out of something that's extremely dense, and will go through just about anything. So,
So, like, even at, like, so the nuclear power plant in Kansas, are they producing plutonium?
so most nuclear power plants are not necessarily designed to produce plutonium. They probably are at some level, but so this is a very simplified version of a nuclear power plant. Nuclear power plants today are much different. I mean, the basic idea is still the same. They're still creating a nuclear reaction that creates heat, and they're using that heat to turn a turbine, to make steam and turn a turbine. But what they're putting in the reactor and how they're controlling the reaction in the reactor is very different. It's usually it's usually an alloy of metals instead of just pure uranium. It's an alloy of different metals that's been created specifically for use in these things, so that plutonium is not made. And the idea there, of course, is you don't want just any person to be able to make plutonium. So the commercial reactors, they're not making plutonium. If they are, they're making such a tiny amount it's not even extractable. But they're trying to. They essentially have certain types of reactors that commercial reactors can be, and then reactors that make plutonium have to be owned by the government. So there's only a few in the United States that are plutonium reactors. I think Hanford, Washington is doing that still. That's the one that they showed a cartoon of earlier. I think Idaho, there's reactors in Idaho that are doing that, I think. There's some in New York, I think. There's only a handful of them, though, that are doing that. But there are so many different kinds of reactors. You could actually take the rods after they're spent. So these rods are kind of actually we took a picture with them once. When we went to the nuclear power plant up in Brownville. This is what these rods look like. So these are your fuel. No, those are control rods. Here are the fuel rods. Here's the fuel rod. So this is what's called the fuel rod are these little things in here, right? And then they have these control rods that come out. So these control rods are made of neutron absorbing materials. Inside each fuel rod, you have these little pellets of fuel, and they're about this big. This is a simulated fuel rod pellet. Here. You can each have one. But these fuel rod pellets are, like you can see, they're only about a centimeter wide, about 2 centimeters long. Let me bring this up on video so you can see it, Zach. Where is it? Here we go. So when you go to the nuclear power plant, they give these out. Wow, that camera's really struggling. What's going on here? Oh, it's because it's looking at the wrong thing. Wrong camera. Let's look at this camera. There we go. Okay, so anyway, this is the simulated fuel rod inside there, and it's just this little thing, right? And it's this on this card. It says this is equal to 149 gallons of oil, 1 ton of coal, and 17,000 cubic feet of natural gas. And each one of the fuel rods holds, I want to say, hundreds of these things. These fuel rods are like 20 feet long, and each one of those rods, each one of the fuel, each one of these guys, what they call this is the cluster. Each one of these clusters holds like 100 of them. So there's 100 of these in each rod or more, and then there's 100 in each cluster. So like 10,000 of these things. So 10,000 of these is equal to 10,000 tons of coal. And this thing is 20 feet long, right? That's a lot of energy. In fact, it's even more than that. But anyway, the point is that it's extremely compact considering how much energy is in it. And then these rods are lowered they're usually in some kind of a pool like this. So this is looking inside of a nuclear vessel. Each one of these little circles down here is a fuel rod, and it's underwater. And the reason it's underwater is because water also absorbs neutrons, so that slows down the nuclear reaction and also dissipates the heat. And so but when they're done with them, this is what happens. They put them in these great big pools of water because the pools of water, of course, keep the reaction slowed down and keep the heat contained, or dissipate the heat, absorb the heat, or whatever. But the problem is this one you can see is full. This thing, there's no more room in this pool. And this is the same one at same thing was happening at the one in Brownsville, Nebraska. It was full when we got there, and that was when I first moved here, which is 10 years ago or more. It was full then, and we got to actually look down into the pool. They don't even allow you in the building anymore. But we actually got to see, the pool was actually over full. It was actually beyond capacity, and they were in violation of some laws at the time because they had nothing else to do. So what they did is they just built some concrete casks out in the parking lot, and now they're storing nuclear waste in the parking lot. Now, why are they doing that? Well, it's like all the other stupid crap that happens in science. It's politics. From 1980, probably 1985 until 2015. So for 30 years, the United States has known that they would need to store nuclear fuel because we don't have a lot of nuclear power plants in the United States, but we do have them. And we were expecting to build more because it is the cleanest form of energy by far. There is nothing that even comes close, not anything. Not even these new green energy things come close to being as clean as nuclear power and as safe as nuclear power historically. And so we knew we'd have to do something about this. And so they started a program where they were, first of all, looking for a place to store the nuclear waste, which of course needs a place. You need a place that's isolated in case you have any leakage. You need a place that is that has a lot of natural shielding because of radiation, and you need a place where some of this stuff can sit for 10,000 years because that's about how long it takes for the radiation to be down to normal levels, to levels that you can just kind of live with. Can also be able to handle a lot of heat. My dad was a part of this project from the beginning. This was my dad's life work, in fact. His life's work was figuring out where to put this stuff, and then once they found a place to help build it and design it so that it would hold this stuff really well. And in 2017, I guess it was, 2000, it was about 1985 till about, no, it was 2007, 2008. It was in 2008 that Congress made the decision to end the project because the best place in the world to store this stuff is in a mountain in Nevada. There's no doubt. This is the best place they found ever. And not only is it the best place, but it's also a mountain owned by the federal government. It's on property for a federal government nuclear test site. So it's perfect in so many ways. It's far away from any living beings of any kind. There's like nothing out there. It's just dead desert land. And it's 100 miles from Las Vegas, and there's no water in between. You have to have water to carry this stuff, any kind of distance. There's like no water. It's one of the driest places on Earth. And this was already at one point a silver mine, and so it was already dug. There was already this huge facility dug underneath the mountain. So they just expanded it, and they did a lot of testing for decades. And my dad did a lot of testing there for decades. and they found it to be perfect. There was just no way that there was going to be a better place to do this. But then the senator from Nevada suddenly found himself in a position of power. He found that the new president was on his side, and the new president was in his political party, and so they got together and decided to end the project. It was one of the stupidest political decisions made in the history of mankind. And that includes some of the stupid decisions that started wars. Because now we have nuclear waste sitting in parking lots at nuclear power plants everywhere in our country. And nobody's been able to reverse this decision. Nobody has done anything to reverse this decision. Mostly because we don't have any presidents who are smart enough to realize it's a problem. We've not had a president that has any kind of education in science in forever. Okay? Like in my lifetime, in my parents' lifetime, and that takes us all the way back to 1940. Okay? 1940s was probably the last time we had a president with any kind of scientific background or any kind of scientific education at all. Like most of them have less science education than you guys do, and they all went to college, Ivy League schools. So their science education ended somewhere in high school biology or something, you know? So you're like, well, how are you ever going to get somebody with enough brain power in Congress or the White House to realize that this is a real problem? And it is a real problem. You can't just have nuclear waste sitting in a parking lot. It's not good. You know, setting aside all the obvious things, there's also terrorist problems. That stuff is a real threat. But anyway, the point is that maybe someday somebody will pull their heads out and put this stuff in Nevada. There really is no better place for it. People are complaining, well, what about Las Vegas? Well, Las Vegas is not threatened by this. It's not going to change anything about them. They don't get any of their water from Nevada anyway. All of their water comes from Southern California, which is in the other direction. And frankly, if Las Vegas was wiped off the face of the earth, it'd probably be a good thing. I don't know. What happens in Vegas stays in Vegas? Is that what they say? I suppose that's not very PC of me to say, but that's a joke. Of course, we don't want anybody to be hurt by nuclear waste, but you definitely want to put it in a place where it's the least impact, or the least chance of being a problem. And it was definitely, that place was the place. There's no way that we could find a better place. They looked all over the world. They looked in China, they looked in Europe, they looked everywhere.
This was 2008?
That was ended in, I don't remember exactly which year it was, but it was early in Obama's presidency. And, you know, like all presidents, President Obama made some good decisions and did some good things for the country, and he did some bad things. He just had the dubious honor of doing one of the worst things that could have ever been done in the history of this country. And that is to just, he set the stage for some major disasters, possible disasters in the future, you know. And of course, nobody wants to be the one that says, well, now we're going to start nuclear or something again, because nuclear is a bad word in politics, right? And so, you know, getting that back going again will be difficult. And of course, we had all the presidents from the 1980s until till the George Bush Jr. years. All of them were trying to increase nuclear power because all of them knew that this was, you know, probably our best bet for clean energy. So every president from like Reagan until George Bush Jr. was trying to increase nuclear power, and that ended as well. In the last presidency. So we were on track to have nuclear power plants online again, and that got stopped. And so all of our nuclear power plants are at least 40 years old. They're all really antiquated. They're falling apart. Like if you go to the one in Brownsville, they've got like lead curtains hanging up in most of the building because they've got leakages everywhere, just water leaks, and the water is radioactive. And so they've got these curtains hanging up in these literally at one point we were walking around a little plastic tape hazard thing, which was essentially a high radiation zone. We were walking around it in our tour. I'm like, this is ridiculous. You shouldn't have a nuclear power plant with just ad hoc, made up safety things. It should be state of the art. It should be up to date. And if it's getting old, you should decommission it. You should end it and seal it up, fill it with concrete, and be done. But we can't. We're stuck. We can't even turn off power plants anymore because of the laws. It's like so ridiculous. Politics has screwed so many things up in science that it's asinine. It's really frustrating to scientists. But anyway, so that's the idea of control rods. Control rods go between the fuel rods. Here's a nice little drawing of how that works in a very basic way. But the control rods can be lowered down or pulled out, and that controls the reaction. You pull them out, the reaction gets hotter, it goes faster. Put them in, the reaction goes slower. And of course, if you have an accident, you drop the control rods all the way in and you flood the whole thing with water. And you hopefully avert any kind of problem. But so anyway, some people often ask at this point, what went wrong with the nuclear meltdowns that we've had in the past? So the three that people like to talk about, there used to only be two that people talked about, but the three now that people talk about are the one in Ukraine, which is what's the name of that town? Yeah, Chernobyl in Ukraine. So what happened there is their design was bad, and I can't remember the exact details, but it had something to do with the controlling of a reaction. You're supposed to design these systems so that if you lose any kind of power, if you have anything go wrong anywhere, that the control rods drop in, and they don't require power to drop in. In other words, even if you lose power, they should drop in, and the reaction should stop. So if anything goes wrong, the reaction stops. Well, they had designed it, and that's actually just a little bit of code in a computer program. It essentially says, it's essentially a Boolean thing that says, if this, then this, if otherwise, then you do this. But the otherwise part of that code is supposed to be the thing that happens no matter what. And so if the power goes off, it triggers that reaction. And the problem was that they had a failure somewhere else in the plant, but that failure actually triggered these things to come on instead of go off. It was designed badly. And they thought they were doing something great with this design, but it was stupid in hindsight. And so it actually created a runaway reaction that was difficult to stop, and they had a meltdown. That is the only full meltdown that has happened in a commercial reactor ever, I think. And even then, it wasn't necessarily it didn't turn into a nuclear bomb. It was a meltdown, and they had some severe radiation release and a little bit of catastrophic mess. But then the second one is 3 Mile Island. That happened about the same time. 3 Mile Island, the system worked just right. They had a problem with the reactor, some kind of thing shut down. Something went wrong. The rods dropped in, it flooded, and it stopped. They had to cover the reactor with concrete, and they had to shut it down for good. But everything worked perfectly. There wasn't a single iota of radiation release. There was no meltdown, nothing wrong there. So 3 Mile Island worked just like it was supposed to, and everybody still freaks out about it. People are still claiming they got cancer from 3 Mile Island, but the cancer levels in Pennsylvania have not increased at all compared to the rest of the country. They're the same as the rest of the country. Nothing has changed in Pennsylvania. Then the third one, of course, is Fukushima. Well, in Fukushima, that was external influences, of course, the tsunami and everything else and flooding. And in Fukushima, the same thing happened. It's worked the way it was supposed to. The problem was that the reactor was built so low next to the ocean that even after the systems were shut down and everything was working properly, the buildings started to flood and things started to break down externally. And so the actual system was compromised. The system worked, but the system was compromised by this huge natural disaster, which caused other problems. And so they did get I think they got a partial meltdown in one reactor or something, but not much of them. But anyway, uh, those are the 3 accidents in 50 years. More than 50 years, in fact. More than 50 years of commercial power plants, commercial nuclear power plants, 3 accidents. And the only one that had any deaths was the one in Chernobyl. Of course, the one in Japan, there were a lot of deaths, but it wasn't because of the nuclear reaction, the nuclear reactor, it was because of the floods and the tsunami. But anyway. So, it's an interesting field of study. Most of the people that work in nuclear power plants are retirement age people. And so there are a lot of jobs opening up in nuclear power plants right now. And the people they're hiring are engineers and physicists, almost exclusively. So they're looking for mechanical engineers, they're looking for chemical engineers, they're looking for nuclear engineers, they're looking for electrical engineers, they're looking for physicists, people who can understand this stuff because they've got a good solid background, can learn the technical, things because they have that background, and then can, take over running these plants.
But why would you want to work for them if the current politics pretty much lead you towards working in a dilapidated reactor, one that's going to progressively get worse over time?
So as far as safety is concerned, there's no real safety hazard working here. They monitor the radiation extremely well. So the things that I talked about, while ridiculous, are not really dangerous to the people working there. They have insane monitoring standards. So, if you even go close to more than you should be getting of natural radiation, they just give you a paid week off work so that you're not getting any more radiation. That's just how it works. But the other end of it is, 6-figure salary.
They're also fairly restricted on their locations because they're only in specific parts of the United States, so you have to move to live there.
Yeah, you definitely had to live near one. So, but that's true of many jobs.
Right, but this is even more restricted because we don't have a whole lot.
Well, they are very specific. Here in Nebraska we have one. We have 2 actually, but the other one is decommissioned. So.
Where was the one you said,
Brownsville, south of Lincoln.
Would you say it's like losing popularity? Will it ever cease to exist?
No, I think eventually people are going to realize that all these green energies we're trying to create are so expensive that they're prohibitive. That's already the case in Nebraska. You cannot build windmills in Nebraska anymore. They did that for a while because the government was paying for you to do it. So as long as it was free to do it, we're fine. But Nebraskans realize that we can't afford wind power. Our electricity is the lowest in the country, and it's almost all coal. Because the windmills that we do have, we're shutting down. We're turning them off because it's too expensive to run unless the government is paying for them, which they were for a long time, for essentially 8 years. We had a president that was and a Congress that was passing laws on green energy that essentially said we're going to use tax dollars to pay for these energies. Well, that's great, as long as they're paying for it. We're going to take advantage of it. But now that they're not paying for it anymore, now that the government isn't subsidizing this, we're realizing that wind power costs 2 or 3 times as much as coal power, and it's not much cleaner. It's just not any cleaner, really. Because you still have to manufacture all those stupid windmills. And that's a dirty process. All those windmills use toxic chemicals to build. They're all made of fiberglass, which is made with essentially fiberglass and really toxic glue. Okay? So these windmills are extremely dirty to build and to set up. And everything else to maintain. Everything about them is dirty. Like, just to maintain those fields, you burn like 10,000 gallons of gas a year. Just driving around to maintain those dumb things. Well, what's clean about that? You trade very clean burning coal, because coal burns much cleaner than gasoline. Okay, so you trade very clean burning coal in one place where you don't have to travel around to do anything with it, to windmills that are dirty to make and dirty to maintain 10,000 gallons of gasoline to drive around between them, right? Because those things are not close together. So, I mean, it's just ridiculous, really, the thinking behind it. The thinking that got windmills started was dumb to begin with. It's like, oh, windmills just grow out of the ground and they take care of themselves and they're like a community. And you know, they're like people that just stand out there and give us free energy. It's stupid. It's stupid to think these things. And this is why they're illegal to build in Nebraska now. Now they've just essentially made it a law. No more windmills. End of story. Because we can't afford the cost in so many ways. So, I mean, power companies, I mean, there's no money to do it anyway. They're not going to build them without the money. But you won't see them driving through town anymore. Like 5 years ago, you saw them driving through town 4 times a day. Not anymore. And you're not anywhere in the country, really, because nobody can afford them. So, you know, and I mean, wind power is going to die off. By the time your kids are around, these wind farms are all going to be dilapidated and dead, unless somebody comes up with some technology that's better than what we got now. Solar power is much more expensive. It's prohibitively expensive as well. Nuclear power is as close as you can get to coal power in price. It's the closest one. It's still more expensive, but it's close. And it takes up a lot less space for a lot more power. So a nuclear power plant half the size of the coal-fired power plant in Sutherland will give you twice as much energy as the one in Sutherland.
You know, I always thought that nuclear power was actually the way to go, just because of not only is it an advancement, but because of how they're set up and because they're actually clean. If you have the money and the understanding to set them up and run them, they're safe and they're capable.
Well, the only thing that makes nuclear power more expensive than coal is all the safety all the safety things that they put on the power plant. That's the only thing that makes it more expensive. If the government didn't have so many safety restrictions on nuclear, it would be cheaper than coal, far cheaper. You know, but you know, what is too much safety? There are some things in those plants that are ridiculous that they're monitoring. Things that they do that are just ridiculous. That doesn't make anything more safe. It just makes politicians feel good about themselves or something. So there's certainly things that could be cut out of the safety process, and it wouldn't change the safetiness of these things. But there's also some changes that could be made that would improve the safety. And for example, getting rid of these old plants and upgrading plants, and you know, all these kind of things. But yeah, I mean, it's politics, and this is the problem with science today: is that science is more politics than it is science. And that's true in every single science that's getting money from the government is driven by the political issues, not by the science, right? I mean, there's nothing more obvious than global warming when it comes to that. Global warming, first of all, we know it happens. Second of all, we have no idea why it happens. Everybody says it's all about carbon. It's not all about carbon. There are like 900 variables in global warming. I'm not even kidding. That's not even an exaggeration. 900 or more different things contribute to global warming. And carbon dioxide is like on that list. If you list them from the thing that affects it most to the thing that affects it least, like carbon emissions are like 685 or something crazy like this. And people are like, this is the only thing and this is the most important thing. So that's two things. I mean, yes, we've known it's always happened. This is not something that's new. The second thing is that the thing that we're focused on is not even the most important thing about it. The third most important thing about the whole global warming issue is that it's a lie. What the things that they're using to tell us about global warming are all lies. They're telling us this is the hottest period in human history, or the hottest period in the history of the world. That is a lie. That's just an absolute downright lie, and they're telling it just hoping that nobody has ever taken a science class. You take any science class, there's at least 100 different times in the history of the world that has been hotter than this time period. Even in the course of the human race being on the Earth, there have been like 20. It's just not true that this is the hottest time on Earth. It's not even close. I mean, there are times on Earth that were 5 degrees hotter, and that's a huge change. So this is not, and they say that our carbon emissions are bigger than they ever been. That's also a lie. carbon emissions, or the amount of carbon in the air right now is actually at a low, but it's rising, so they're freaking out. I mean, a few thousand years ago, 100,000 years ago, it was like 10 times higher than it is now. And the amount of carbon in the air is the other thing. They tell you this like this is some huge amount of carbon in it. It's less than 0.5% of the air. It's not that much carbon. It's not like this thing that's just going to choke us out. So they make all these exaggerations to make money. That's all it is. It's all about making money, because if they get people frightened, people think it's an important thing. The really crazy thing is that there's probably nothing we can do about it. There's probably zero that we can do to change this trend. Because are people going to stop driving cars and flying airplanes? No, they're not. And is there an alternative to gasoline for those things? No, there is not. You know, you can try electric cars, but guess what? Electric cars get their electricity from coal. You know? And we've already decided that we're not going to switch over to nuclear, so coal is our thing. So we're talking about all these things that are so important and so bad. And first of all, the things we're talking about are lies to make money, both from the citizens. The citizens give their money up in taxes and support for political leaders, and all political leaders are guilty of this. Doesn't matter what side of the aisle they're on. Doesn't matter what political party or leaning or whatever, what state they're from. They're all guilty of this in one way or another. They find something to get the public all riled up about, and they lie about it, and they get some scientist to come on and lie about it. Saying a lie might be a little strong, but it amounts to the same thing. They just exaggerate things, and it's ridiculous. And so they exaggerate and exaggerate, and people get all freaked out because they're ignorant. And then we have these crises, that supposedly people are getting angry and killing each other over global warming. Holy crap! What a stupid thing to get angry about. Can't do anything about it. In fact, if you get angry about it, you're going to increase carbon emissions out your big old fat open mouth. Then you're gonna cause the problem that you're trying to. I saw this super funny comedy thing where these Amish people were gonna go green, and they decided they were gonna stop walking and stop talking because it commits more carbon to the greenhouse gases of the earth. It was just hilarious.
So have you seen an inconvenient truth?
I'm sorry?
Have you seen an inconvenient truth?
No, I don't watch political mockumentaries, which is what that is. That's just a joke. I don't. Yeah, who made that? Al Gore. Yeah, talk about somebody who's ignorant. Al Gore doesn't know anything. Al Gore was made fun of when he ran for president because he misspelled simple words in his campaign stuff. Like he was speaking to people in Idaho, and he had this thing that he released to the press, and he was so proud of writing his own speeches, and he misspelled potatoes. I mean, are you kidding?
That was Quayle.
What's that?
It was Dan Quayle who misspelled potato.
Dan who?
Quayle.
Oh, was it Quayle that did that? I thought that was.
Yeah, he was the one who misspelled potato.
Oh, who's Dan Quayle? I can't remember what year he was from.
He was George H.W. Bush's vice president.
Oh, right. Well, anyway, the point is that they're all kind of dumb. They're not. Their science is not at any level what it should be, right? But the point is in politics is that if you have these people that are just not scientifically educated making these decisions, you're going to get all kinds of problems, and that's what we're dealing with in science today. Like I said, I don't follow politics all that well, so I never watched that movie and never wanted to because it's not a scientific movie. There's no doubt about that. The only scientists who have ever said I approve of this movie, all of them have been political appointees. Every single one. Every single one of them has worked in the White House. Every single one of them has worked at Congress as political advisors. And anytime a scientist acts as a political advisor, they become part of the system because they're essentially getting paid. They're essentially getting paid for their scientific opinion. And they get paid a lot. Scientists can make millions off of giving political opinions. And it's really bad. Scientists who start doing that really mess up science for the rest of scientists. So I don't like Who's the guy that makes the other all these other documentaries, supposed documentaries? What's that?
Michael Moore.
Yeah, Michael Moore. He's done a bunch of these things. So yeah, he's another person that I just ignore entirely because they're not. I mean, it's kind of ridiculous. I mean, global warming is the perfect example because it's the latest one that has kind of overtaken the world. It's not the only one that has had a problem with this. It's just the latest one. But the scientist who started the whole global warming trend, he actually coined the word global warming. He actually came out and admitted that he'd made up his research. He'd made up his findings. He'd actually made up the data. The data didn't actually exist. He actually just made it up. And he'd retired and he'd made millions off of it, and he just kind of admitted it. It was just kind of weird. Why would you admit that? He's a guy from Sweden. I don't remember his name. But he came out and said this, and it just got buried by politicians. They just kind of like swept it under the rug and didn't talk about it, and just kept pushing global warming. And scientists all over the world came out and said, this is unethical. This needs to change. We can't have politicians allowing this to happen. And they just kind of ignored it and kept sweeping under the rug. And it frustrated them. I mean, it was all over Science News, but it wasn't anywhere in the real news. Like if you read Physics Today, or if you read Prism, or if you read Science News or anything like that, you saw it there. But only a few people read those, you know. So it just kind of got buried and lost, and nobody talked about it. And it frustrated a lot of scientists because scientists generally aren't really that excited about politics. But when politicians get in to the science and change what's going on in science, it really pisses them off. But, you know, scientists are just kind of... Scientists are, I hate to say we're, because I'm technically not a practicing scientist, but scientists are often portrayed as this weird group of people that don't really have an impact on real life because they're kind of separated, because they're weird, nerdy people and they don't really live in the real world. But the truth is that scientists have a tendency to be quite practical people, normal people that you wouldn't even know they were scientists. But they get ignored. They get ignored that way as well as when they're actually playing the role as scientists. And so it's like getting kicked in the face twice, you know. They get ignored because they don't look like a scientist, and then they get ignored because they are a scientist, right? I don't know. It's kind of since I grew up in a scientific community, I just saw this over and over and over again, and it was just monumentally frustrating to the scientists that I grew up with. I'm trying to remember, there was another incident in the 80s in my town. Well, it was when Ronald Reagan was president. He came to visit our town because we have these two big labs, his whole Star Wars plan. And the scientists there were all frustrated about this Star Wars issue because, you know, it was another one of these political stunts that just made no sense. And later on, we discovered that it was literally a political stunt. That it was just, you know, it was just politicians trying to play power games with Russia or whatever. And you're like, oh, gracious. And they put these scientists in between. So a lot of these scientists actually kind of lost their credibility in the scientific community because they jumped on board with this whole Star Wars idea because it was money, it was funding. It was something that they gave them money to do their work. And it's, I don't know, it's just never-ending cycle. No matter what the political party is that's running things, everybody takes advantage of the science community to push their agenda. And unfortunately, many people in the science community jump on board because, you know, money makes the world go round, unfortunately. So it becomes, this never-ending problem. Anyway, I find this stuff fascinating. I can never get enough of science doing really cool things in the world, and I think nuclear power plants are one of those things. Let's see here. Where were we? Where's my video?
I think it's below your stop share green.
Ah, yes. I hate this thing. How do I get this to go away? There we go. Let's watch some more.
Thus, the reactor itself can be a source of atomic fuel. Besides producing plutonium, nuclear reactors also make possible very important peacetime uses of atomic energy. Remember that the chain reaction process in a reactor creates tremendous heat, which scientists have learned how to control.
So I'm going to move us
Probably
back
the
to where
most
we were
important
here
use
further
of
on.
heat from nuclear fission.
The Atomic Research
Invisible
Laboratory.
detectors aiding the cause of science in many different fields. In agriculture, radiation is now used to test such things as the effect of fertilizers on plant growth and the proper timing for their use, helping to assure bigger and better yields from tomorrow's farms.
So this actually, so Zach, I did send some lab equipment to you, and I sent the lab to Micah. And I did, what I sent is some nuclear samples and a nuclear sample generator, a radioactive sample generator. You'll be able to make your own short-lived nuclear or radioactive sample. Well, I forgot, did we put that little plastic tray in that thing? Okay, so that's in there. So anyway, so you'll be able to make your own short-lived radioactive sample. It has a half-life of, I don't know, a few minutes. And then you'll be able to measure it using a Geiger counter, which I also sent with you. It was with that box. So that should be there today. It should be there already, in fact, I think. So just so you know, you'll be able to detect your own
Radiation has
radioactive
found literally
isotope.
hundreds of new uses, such as the automatic thickness control of sheet aluminum, saving hundreds of man-hours of labor and assuring accuracy never before possible. In the fields of medicine and biochemistry, radiation is performing near miracles of diagnosis and discovery. With radioactive sodium, doctors are solving more of the seeming mysteries of heart disease and circulatory disturbances. Radioactive phosphorus has been used to locate tumors in the brain and greatly simplify operations for their removal. Iodine-131 finds one of many uses in...
So these different things. So the biological side of this is quite interesting as well. Again, I'm no real expert in it, but from what I understand, the different organs in the body and different systems in the body will interact with or absorb or kind of hang on to different chemicals as you put them in your body. So, for example, in this case, you have iodine going in and it gets into the say this is the thyroid or something like that, but anyway, whatever this is, and it kind of gets stuck in there, and because it's radioactive, it's giving off these gamma rays essentially. You can detect that using a Geiger counter, and you can see different things. You can essentially get a representation, an image, you could say, from these gamma rays of the thyroid. Also, diseased things like cancers also react differently or behave differently with some chemicals. And so you can start to find, cancerous tumors and other things like that. You can also treat them. What's your question?
So the tumor itself is not necessarily radioactive; it just reacts differently with some.
Yeah, so tumors behave differently with different chemicals. And like I said, I don't know all the details. I'm no expert by any means, but it has something to do with their metabolism and their actual makeup, what their actual cellular structure is or whatever else. And so you can actually detect different things in the body just by putting different chemicals in the body that are radioactive, right? So because they're the different chemicals, they will do different things in the body, but because we make them radioactive, before we put them in the body, we can detect them. So if you have a chemical that has a tendency to sit inside of a tumor, then you make that chemical radioactive, put it in the body, and then try to look for it, see if it stays in the body. If it stays in the body somewhere, there's a good chance there's cancer there or something like that. And it's not exactly that simple. There's much more involved with it. But I mean, the basic idea is that we always are putting chemicals in the body. If we can make them radioactive, we can track them. Because otherwise, chemicals are extremely difficult to track. For example, in the airports, when they're trying to look for explosives, still their best method for looking for explosives is still using dogs. It's not practical to have dogs in the airport everywhere sniffing, but they do have them sniffing the luggage out on the tarmac. They do have dogs looking at luggage there, because that's still the best way, because detecting them using some kind of machine is extremely difficult and extremely unreliable. Okay, so have you ever been in one of those things that has the puff of air that goes through your clothes? No, there's a machine that is designed to look for explosive chemicals, and it has to essentially blow a puff of air through your clothes and then capture any dust, and then it puts that through what's called a mass spectrometer to look for specific chemicals. Extremely complicated, involved, and expensive test to do. So they don't do it. They used to do it all the time right after 9/11, a few years after 9/11. But I went through it. I don't know how many times, but I've not been through it in a while, so I assume they're not around much anymore. But anyway, the point is that these, these chemicals can be detected much more easily once they're radioactive, because of course radioactivity is easy to detect. So.
Revealing conditions of the thyroid, and there are many more. New ways of using radiation are being discovered constantly through the tireless work of modern pioneers in such fields as chemistry, metallurgy,
Okay, the rest is just
medicine,
propaganda
and
by GE, of course, which is pretty much this whole movie. But I like this movie because it's so simple, but it really does touch on the really important points. If you get into other movies, they either get too technical or they just don't cover all the stuff that you really want to cover in something like this. One more thing that I'll point out is the really interesting thing about these medical uses is that you don't want that radiation to kind of damage the body, and you don't want it to hang out in the body for very long. So a lot of times these radioactive chemicals that are used in medicine have a very, very short half-life, which means getting them to the hospital is actually quite a challenge. Because once you create them, they have this short lifetime, and then they're useless. Sorry, did you say something, Zach?
No.
Okay. So, and the other thing that's kind of funny is that, again, because of politics, these things have not been made in the United States. I think they just started making them in the United States recently. And I don't remember when that started, but for the longest time, the only place that they were available close to us was Canada. So there were a couple of nuclear reactors in Canada that were specifically designed to make these things for export to the United States, because it was illegal to make them in the United States for some reason. I don't know, another political thing. But anyway, the point, the funny thing about that is that this is actually what made these things so expensive. These nuclear medicines would have to be made at the reactor and then immediately put on a plane, just a small plane that was right at the reactor, right at the nuclear power plant. And they would take off from the nuclear power plant and land in a city that does these nuclear medicine stuff, and then they would distribute it then at that point. And they came up with a better way to do it. They started making nuclear medicine generators. So they would make something that's a little more radioactive and has a little longer half-life, and then they would take that to the hospital, and then that would be used to radiate other things. And so that can be done as well. For example, at our hospital, they do that all the time, where they have this thing, essentially this radiation room, prep room, where they radiate different things for use in the body. So they've actually got a sample, a radioactive sample in that room that they can put things in with that sample. It's contained in a lead box, and they put other things in that lead box with it for a while, and they get irradiated. They become radioactive. So that's a better way of doing it, because then you don't have to rush it everywhere. But still, it's kind of interesting, the industries and the innovations that this has spawned, this crazy radiation thing. Now I have I've tried to find the person that I have to talk to get our tour at the hospital. I've not been successful to contact them yet, but I'm going to continue doing that today. Just so you know, what time is it? Are we running out of time? No, we got plenty of time. Okay, so let's actually go to our book for a little bit and see what we can see about the nuts and bolts of this stuff, so that you can maybe do a little bit of homework and understand some things. That would be fun. So, if you've ever been to the Air and Space Museum in Omaha, they actually have a World War II bomber that you can tour there, and their dials actually have radium paint on them, so that they could see them in the dark, right? And the radium, of course, is a radioactive. It's a radioactive element, and one of the things that it does as it radiates, if it radiates near something that is phosphorescent, in other words, something that will absorb that radiation and then re-emit it in some radiation in the visible spectrum, then it will make that glow. And so they mix the radium in with the paint. The paint has phosphorescent chemicals in it, and then the chemicals actually glow. It's not the actual radium that's glowing, it's the chemicals that are glowing, which is kind of interesting. Yes?
Have you heard there's an article called Radium Girls? Something. It was the women during World War II that were in charge of buying this,
Oh, no, I've not seen that.
and they weren't aware of the date.
All the
names
side
of it.
effects, yeah.
Like, they put it on their teeth and then go on dark green. But years later, they started losing teeth.
Oh, I haven't heard of that. That's kind of weird.
Interesting.
So they painted their teeth with radioactive paint.
Or like their dresses.
Yeah, just to have fun.
Yeah. They didn't know.
Yeah, there were a lot of things we didn't know about radiation during World War II, unfortunately, and a lot of accidental problems in post-World War II as well. There were a lot of testing done, nuclear weapons and radiation post-World War II during the Cold War that was just horrific. Just the things that they did. Let's just put 1,000 soldiers in a trench and explode a nuclear bomb a mile away from them and see what happens. And a lot of that stuff is, we don't really know the details of it, but it certainly was not good things that were happening. So, but again, political decisions, right? Who was president? Whoever was president during that time, might have been MacArthur, might have been, who knows who it was, but they were making some goofy political decision based on some goofy political idealism, and dragging science into it and hurting people. So, and hurting science really. But. So anyway, here's an interesting experiment that was done early on with radiation. So if you put like uranium or plutonium or something in here that's radioactive, and then you put a strong magnetic field outside this lead box with a hole in it, the radiation that comes out will be split into 3 groups. You'll have one group of radiation that will turn a lot in the magnetic field. So it gets a huge turn, and then it hits this screen over here. And then you get this this type of radiation that comes straight through and hits the screen. It doesn't get turned at all. And then you get one that gets turned a little bit, not maybe as much as the other, and hits the screen. And doing some calculations, so calculating, they did know, of course, at this time. This is 100 years after this was discovered, but so this was actually done in the 20th century, very early on in the 20th century. But it was well known before that charges moving through a magnetic field will turn. So they figured that 2 of these particles were charged particles, and that one of them was positively charged and one was negatively charged. And they could even tell which one was which. They knew that this beta particle was negatively charged because it turned left in this magnetic field as it went through this way, according to the right-hand rule. And they knew that this alpha particle was positively charged, of course. But by doing some simple math, they could actually figure out the mass to charge ratio of each of these as well, which was done in the same way that the electron charge to mass ratio was done. And they discovered that the beta particle was actually an electron. And they discovered actually that the alpha particle actually was 2 protons and obviously had 2 neutrons in it, which they were just discovering in the early part of the 20th century. They didn't actually have it discovered at this time. But it essentially had the mass of 4 protons, but only the charge of 2 protons. So it was when they started to discover that there was another particle about the same mass as the proton that had no charge, right? So the alpha particle, of course, is a helium nucleus, 2 protons, 2 neutrons, and the beta particle is an actual electron. But the problem is that, you know, this stuff inside the lead box didn't become charged when it released these things. It wasn't releasing these electrons and becoming all of a sudden positively charged, right? And the alpha particles, when it released the alpha particles, there were other electrons that were released, but they weren't high energy electrons. So those electrons were accounted for. So this electron right here was the mystery. Where is it coming from? And that's the one that I told you about earlier, where there's an actual process where a neutron can actually decay into a proton and an electron. And that's where that high energy electron comes from. It's from that decay process. So down inside of here, there's something going on where there's a proton being created from a neutron that's decaying into a proton, a neutron decaying into a proton, there we go. And this is becoming a natural transmuted element, right? It's going from uranium to neptunium, maybe, or something like that. Anyway, so they also discovered that these different types of radiation have different penetration abilities. For example, alpha particles can be stopped very easily. It takes a little, thin piece of paper, just a little bit of air. Doesn't penetrate into the body very much. But they're fairly massive particles, so they can actually do some damage in that short distance. But they don't really get through things very well. The beta particles, which are the electrons, turns out they can be blocked by most metals. A thin aluminum plate will do it, or if you're trying to block it with your body, it'll penetrate into your body a fair depth, but won't necessarily go through your body. But the gamma rays, it turns out, it takes a lot of something in the way to stop them. They'll go through just about anything unless it's a very dense metal or meters of something less dense like concrete. So gamma rays really travel through just about anything.
So what was in the video, what were they doing with the aluminum foil? Running radioactivity?
So the radioactivity will go right through aluminum foil, right? But it will be attenuated a little bit, so it doesn't go through perfectly. If you have a radiation of, say, 50 sieverts on one side of the aluminum foil and 35 or 45 on the other side, if you keep that difference the same, then the aluminum foil is the same thickness, right? So they were using it to actually determine the thickness of the foil, and then they used that to control the rollers that were making the thickness of the foil. And what that does for you is it saves you money. If you can roll your aluminum foil is an extremely used product. Okay, it's a multi-gazillion-dollar business out there. I mean, it's bigger than cars. Like, could the car companies, all the car companies in the United States, probably don't make as much as aluminum foil companies make in the United States. That's just a guess, but I mean, it certainly could be true. I don't know if it is actually true, but I'm guessing that it's not true. It's just aluminum foil is used by so many different industries every second of every day, right? So if you can make aluminum foil extremely thin, very consistently, then you can make money, right? But the problem is if you make it just a little bit too thin, it falls apart. Right? If it makes it too thick, you're wasting money. So they tried to make it as thin as possible without going too thin, but then they would have breaks in the foil. The foil would be good for a while and it would be bad for a while. So they would just make it thick because it just wasn't worth it. But it was costing them money, With this process, they could track how thin it was very, very carefully and adjust the process during the process to make it. So it probably saved them millions at that time. And that was a while ago. So. But kind of things like that are actually those are the unsung heroes of technology and science, making things more efficient, more affordable, more whatever, right? Little things like that contribute more to the human race than big things for the most part. You know, the iPhone probably didn't make as big an impact as that aluminum foil thing did back in the 50s. that's probably it sounds like a strange statement. It's probably true. Just so many people were able to improve their economic situation and everything else from all the jobs and everything that were created in one little industry like this. So anyway. Let's talk about, let's see here. Okay, so here they talk about ionizing radiation. And so ionizing radiation has to do with the amount of energy in the radiation. If a radiation particle, whether it be a massive particle or a non-massive particle, if it has enough energy to come in and knock electrons out of molecules, we call that ionizing radiation. So the radiation has enough energy to displace electrons. And that's a problem because once you start displacing electrons in molecules, then the molecules become highly reactive and they start to do things that they shouldn't do. And that's the last thing you want to happen inside of your body, is to have your molecules doing things they shouldn't do. We call that cancer, right? So in essence, ionizing radiation is the way that we define dangerous radiation, okay? Now, ionizing radiation is something we encounter all the time. Go outside on a sunny day and even a cloudy day, and you'll encounter ionizing radiation. That's why skin cancer is such a prevalent cancer. It's, I think, the most common cancer on Earth. But we want to try to avoid that. Our body can handle a certain amount of ionizing radiation on average. The average person can handle just so much ionizing radiation without getting any serious kind of problems happening. And so we try to keep it underneath that amount. And they're showing what they call a dosimeter here, which essentially measures the amount of ionizing radiation using ionization actually. It's so in this dosimeter, this is essentially a Geiger counter, but Geiger counters are specifically designed for counting, not measuring the amount of energy. But inside of this tube, you have essentially a high voltage potential between the center of the tube and the outside of the tube. So down the center of the tube, there's usually a wire, and then in the simplest form, and then the outside of the tube is the other end of this potential. And with this high electric potential, if you get radiation coming in, it will be accelerated towards one end of that potential or the other, depending on the charge of it. And if it's not a charged particle, like a gamma ray, it will just go straight through and hit the metal anyway. If it goes through and hits the metal, it will hit the metal and it will essentially create some electrons. If the charged particles hit the metal, they will also release some electrons. If the charged particles hit the wall, they will also release some electrons if they are high enough energy. So no matter what comes in here, it's going to release some electrons. And depending on the number of electrons it releases, and there's some more details to this with some cascading effects and other things, but the end result is that you get an amplified signal at the other end that tells you that's calibrated to a range. If it's above a certain amount, then that's considered ionizing radiation. Below a certain amount, it's considered non-ionizing radiation. And they can tell, whether or not in this case, it looks like, I don't know what they're actually. So this could be a lot of different things, whatever it is. But obviously, this little piece of metal in here is radioactive, and they're measuring how radioactive it is. I don't know what it is, but it's something. So anyway. Here they show some They show a decay, the beta decay as they call it. How do you make it go? There you go. There we go. So that happened very quickly. But anyway, so that I put in the hydrogen like this, right? So I,
You can push +10.
yeah, plus 10. There we go. So I put in these hydrogens, and if I press play, what happens is they decay, and when they decay, they become heliums because one of their neutrons becomes a proton and releases an electron, right? But these haven't changed in their charge. They didn't lose an electron from their shells of electrons. They just lost an electron out here, right? So, well, they don't change it. They don't change in their external charge, but their overall charge will change. Because if they lose an electron here, or if they lose a neutron here and gain a proton, then they have two protons and only one electron orbiting. But in the same metal, in the same situation, you have, if this isn't a metal, obviously, because it's hydrogen and helium, very difficult to make those into metals. But if this was inside of plutonium, for example, at the same time you would be having alpha particle discharge or alpha particle decay, and that alpha particle decay results in two electrons that are free and low energy and can be recaptured. And overall, they account for them. They essentially do account. It's like an accounting job with atoms, but the electrons all work out, and you get extra electrons from the neutron decay. So. Who knows what this is? That's releasing all kinds of things. Measuring the half-life. So anyway, measuring the half-life is something you'll be doing in your lab today, Zach. We did it yesterday. You're going to measure the half-life of dice. Okay, so here they show another Geiger tube. This is actually a Geiger counter, so instead of measuring energy, it actually just counts the number of events that happen. And this dial here is essentially just a counter. You can do it in frequency, or you can actually do it in direct counts. And it's a little bit similar to the one I'm sending you. Mine's a little smaller, a little newer, and it's only one piece. But essentially, you can set it up to beep every time. Here they show this tube with the wire down the middle, right? Talk about the cascading effect as well. It's all here they do another decay thing here. That's fine. I actually want to talk more about isotopes now, since we've come towards the end of this here. So here's an example of dealing with isotopes in okay, here we go. In the periodic table, you have your name of your element, and that's going to be this X thing. And normally in your periodic table, you just have a let's see, what do they call it? The atomic number, right? So the atomic number in this notation here, this is what we're going to use for nuclear science, is going to be Z, I believe. Yeah, the atomic number is Z. And then you have these other two, which the A and the N in here, right? So the A is going to be the total mass number. So that's the number of protons plus the number of neutrons. So if this is, let's see, carbon, this could be a carbon 14, which would be A is equal to 14, but carbon is always equal to what on the periodic table? 6. So it would be carbon So would be C, the A would be 14, the Z would be 6, and how many neutrons would we have? 8, right? Turns out that carbon-14 is actually unstable and has a half-life of something like 4,000 years or something. And that's what they use for carbon dating. Right? Carbon dating is using the amount of carbon-14 left over from something that's died. Right? And then we have the N here, which is related to A and Z. Let's see. A is the notation. What do they call it? Oh, it's number of neutrons, right? So they don't. I guess it's just called the neutron number, right? This one is not always used. In fact, it's almost never used since you can get the neutrons from these other two. So here are just some information you might need here. The mass of protons and neutrons almost the same, not quite. Neutrons a little bit more than the proton. And this was often thought, this is one of the reasons that people first thought that a neutron was actually made of a proton and an electron together, stuck together somehow. But there's no evidence of that at all. The mass of the electron plus the mass of the proton does not equal this number. There is a difference. There is essentially a mass defect, you can think of it as, but it doesn't match up even for some kind of fission reaction. It doesn't match up for that. So there's no evidence. The evidence actually points to the neutron being its own particle, and that it can decay and it can create, essentially give birth to, you can think of it as an electron, and decay into a proton. We'll learn more about that, how that works later. The theory of how that works, rather. Here's the electron mass, very, very small. U is essentially what we call the atomic mass unit, and it's equal to 1.00726, the mass of a proton. It's essentially kind of almost like an average between proton and neutron and the mass defect in atoms. It's based on carbon. Again, this is because carbon was thought to be the most important atom in the universe, because everything, biological was based on carbon. And they discovered later that maybe that's not the best thing to do, but they stuck with the notation anyway. Excuse me.
A mole is based on carbon.
Yes. Moles are based off of carbon. Everything's based off of carbon and water and biology and chemistry. So. Then we have the mass in mega electron volts c squared. This is a weird unit, but this is the unit that particle physicists use. And the reason for it is because it actually makes more sense to them to measure everything in electron volts and versions of electron volts rather than all these different things like kilograms. Because remember that kilograms and meters are based on standards. They're not based on anything real. But electron volts actually are. The speed of light is something that is based on scientifically determined things. So we know that the speed of light is constant in a vacuum, and we know that the electron volt is a very specific unit of energy measurement, very scientific unit of energy measurement. And so if you can define your mass this way, this actually does come out as a mass, I believe. Let's see, I can't remember all the units of electron volts, but anyway, you can measure your mass in mega electron volts c squared, and you get 938 for the proton, 0.5 for the electron. Kind of tiny. So, using some things from the previous chapters in atomic physics and everything, they do some calculations for the radius of the nucleus, for example, 4.6 femtometers, pretty tiny. Remember, the atom is angstroms, which is 10 to the minus 10. Femtometers is 10 to the minus 15. So this is more than 1,000 times smaller than the actual atom itself. Kind of small. Actually, it's about 1,000 times, because it's half an angstrom is the size of the half an angstrom, which is 10 to the minus 11 ish. 5 times 10 to the minus 11. This is 5 times 10 to the minus 15. So it's about 10,000 times smaller than the nucleus, than the entire atom, rather. Then we get to this thing. This is really kind of the big deal. We call this the table, the chart of nuclides. And this chart has number of protons on the horizontal axis, number of neutrons on the vertical axis. And then it charts out this big thing that I like to call a banana slug. Yeah. Because when I first taught nuclear science, I was teaching it at the University of California in Santa Cruz, and their mascot is the banana slug. Talk about weird mascots. But banana slugs are a very large slug. They can be anywhere from 2 or 3 inches long to 2 or 3 feet long. And they're yellowish, brownish, greenish in color. And they live in the forests, the redwood forests of California. And so this is the chart that I used the first time in this big yellowish thing. But this is what a banana slug looks like. So I just couldn't help myself. See? And if you ever go to California, they'll ask you if you have ever kissed a banana slug. That's like the thing to do, is to catch a banana slug and kiss it. They're bigger. They're as big as snakes. They can be very, very large. They're really kind of gross sometimes. But yeah, banana slugs are very much a thing of Northern California. Ooh, somebody's eating one. Roasted banana slug. Anyway, the point is it looked like a banana slug, so I call it the banana slug chart. I like this one. Let's look at this one here. So this chart was put together, it's still being put together, in fact. It's a really good way of looking at the different types of nuclides out there. So what is a nuclide, first of all? A nuclide is, nuclides are all the different types of atoms out there that have been observed, either observed naturally or observed by something that was created by man, whatever, those artificially created atoms. On the chart, you have these different color regions, and of course you have Z here. So if you move this way, you're moving up in protons. So you go from let's see. Actually, this one has protons on this axis. This one does it backwards. That's fine, doesn't matter. So we're going up a number of protons here and number of neutrons here. So if you're at 1, this whole row that's at 1 is helium. So if we zoom into it, which is what we're going to do next, let's see. Used to be able to. Sorry, what?
Go back on one page. Bottom right, it looks like there's a zoom.
Oh, yes. No.
Oh, it's not. It's false advertising.
Yes, indeed. There's an interactive one, and I can't remember where it's at. Let's see if I can find it. Interactive. Here we go. That's got to be the one. The Nuclide Explorer, they call it. Are you kidding? You have to buy access to it. What is this world coming to? This one's live chart of the nuclides. All right, that's good. That's what we want. Okay, so now if you go here, so this one is this one looks like it's neutrons on this axis, protons on this axis. So if I start way down here at 1 proton, 1 neutron rather. There's 1 proton. So protons are actually, yeah, protons are on the y-axis. If I go up 1, I go up to the next one. So this is 0 protons and 1 neutron. It's just a neutron, right? This one is 1 proton, 1 neutron. So that's hydrogen, right? And they give us all the interesting information about it. They tell us, for example, to tell us the half-life. It says it's stable, so there's no half-life. They tell us the abundance, how much of all of hydrogen, how much of it is just 1 proton. 99.9885% of all hydrogen is just 1 neutron and that's it. 1 proton and that's it. But if we move over 1 here, whoa. To 1 neutron, 1 proton, this is hydrogen 2, right? When we say hydrogen 2, I mean that's got a total mass number of 2. That means 1 proton, 1 neutron. It actually does have, let's see, it has some different interesting numbers here. The abundance is way low. It's very 0.0115%, 57%, but it's also stable. This is called deuterium. Now deuterium, I think I said deuterium is radioactive, but it's not radioactive. Tritium is. Whoa, how do I get there? Ah! There we go. So let's go to the next one. So tritium, this is hard to. There, that's hydrogen 4, I want hydrogen 3. Hydrogen 3. Helium. Hydrogen 3, there we go. So hydrogen 3 actually has a half-life. The half-life is 12.32 years for hydrogen 3, which is called tritium. So that one's radioactive. That one actually glows in the dark. It's a liquid. In normal conditions, it's a liquid. And that actually right there is the most expensive substance on the planet by far. If you had 1 cubic centimeter of that, 1 milliliter of tritium, you might be the richest man on earth. That stuff is completely just beyond value. It is the stuff that they use to make nuclear bombs, essentially, with it. They actually paint it onto really expensive watches for divers' watches. They put it on the hands, but it requires only a few atoms, like 100, maybe 1,000 atoms. So it's like almost none, and it will make the hands glow on the watch. But it'll still make that watch cost $5,000-$10,000 just to have a few hundred of those atoms on there. But it's a very rare substance, very difficult to make. It has to be made in a specific type of nuclear reactor under specific conditions, and it's used to make hydrogen bombs. It's a really, really expensive substance that has a very, very specific use. It's also used in other fusion experiments. Here's hydrogen 4 with 3 neutrons, really, really unstable. Out here, these half-lives get really small. They don't even measure the half-lives in seconds anymore. Like this one that's measured in mega electron volts, which is a small, tiny amount of time. The half-life is so short, it's nearly immeasurable. Here's one that's 806.7 milliseconds half-life, very short half-life for helium-6. 2 protons, 4 neutrons. All right, here's 2 protons, 3 neutrons, helium-5, half-life of 0.648 megaelectron volts, and then very, very tiny. So essentially you've got all these things here, and the black things down the middle, all the black ones, I think are the stable ones. Yeah, over here it says right here, the stable ones are black. The naturally occurring ones are mostly down the center of here as well. Not all of them, but most of them are. Some of them are a little off-center, because there are some naturally occurring radioactive things. But then you have different kinds of radioactivity. So anything that's alpha decay, in other words, it gives off a helium nucleus, are these yellow ones up here. Then you have EC and beta, EC positive and beta. I can't remember what EC positive is supposed to be. Is that positron? It might be positron. Yeah. Well, those are the green ones here. And then you have your beta particle ones. Those are the bluish green ones down here. And then you have a proton emitter. Or is that positron? How come they don't have them actually written out? Anyway, so this one's, I think this one must be, I think this is, so this EC plus beta plus is actually a positron. I think this one's a proton. So a proton actually comes out. And then you have a neutron emitter. And then I'm not sure what the EC and SF are. I can't remember now. And there's actually even more than that, I believe. Oh, here they have them. No, they don't. They don't list them there. Anyway, electron cloud. Anyway, but all the different types of decays. Now, this is not even the most interesting thing about this. This and the most useful thing about this. There's lots of information here, but there's actually even more than you think. So let's go to any spot on this table. Let's go right here. This is can't read it because my stupid thing's in the way. Francium. So this is francium 1. This is francium 217. It looks like 217. Francium 217 has a half-life of 22 microseconds, and it tells us what kind of decays it has. It has alpha decay, beta decay. It has the EC decay, NNP decay. So it has all these different decays that it will do. So if it goes through, let's say that it goes through alpha decay, what is it going to become? What's going to happen to it? Well, if it goes through alpha decay, it's going to lose what?
You said helium.
So 2 protons and 2 neutrons, right? So if you lose 2 protons, what is 2 protons less on this chart? Well, protons are up and down. So if we lose 2, we'd have to go down 2. So if we go down 2 from francium, that takes us to radon and then to actinium. Okay? But then we also lose 2 neutrons, and neutrons are on the horizontal axis, so we'd have to go to the left 2, and that tells us where we would decay to. So alpha particle decay, you go to the left 2 and down 2, and you'll know what the decay product is. This is called the daughter of the decay process. I don't know why they make it the daughter, but they do. Why not just, well, anyway, the product. Anyway, this one becomes actinium. Let's see, N plus Z is, so this is actinium 213, it looks like. Right? So what if, so this one will do, so this one will do beta decay as well. What is beta decay? It's when beta decay is when you spit out an electron. So what happens in the nucleus when you spit out an electron? A neutron decays into a proton and an electron, right? So that's beta decay. A neutron decays and becomes a proton and an electron, and the electron gets kicked out.
So it just means a proton.
It gains a proton and loses a neutron, right?
Yes.
So a proton, it gains a proton, so you gain a proton by going up, you lose a neutron by going left, and you become radon 213. Notice that before we were actinium 213, now we're radon 213. We haven't lost any number of particles in our nucleus. We've just changed one from neutron to proton, right? And expelled an electron. So that's beta decay. Of course, gamma decay, which this one also probably does. Yeah, so at the bottom, the major radiations, it has 2 gamma radiations, which are 854 and 545 kiloelectron volts. So if it does a gamma decay, it doesn't lose any particles in its nucleus. It's like the particles just kind of rearrange themselves and get more comfortable, right?
With gamma decay?
Yeah, gamma decay, remember, is just like an X-ray. It's not a particle of mass. So the nucleus doesn't lose any particles in gamma decay. It does lose energy, but it doesn't lose any particles. So it's kind of like, it's really just kind of like they're rearranging themselves to get more comfortable. So lower energy, it loses some energy in the form of gamma ray. And so it just stays where it is. It doesn't change its isotope. So each one of these is a different isotope or a different nuclide. It's often pronounced nuclide, but it's spelled nuclide. Anyway. And notice that here in the middle of the chart, there's a lot of different nuclides or isotopes for each atom, right? So this right here is tungsten. There's a bunch of different ones in here.
Tungsten's great.
Tungsten's quite interesting. Look at this. There's a blank one right here. There's a blank spot in tungsten. Why is that? It's never been observed, right?
Must be too unstable.
It could be extremely unstable. It could be something else, but it's just not been observed. So, and you can see, of course, there's more blank spots in other places.
You know, this does look a lot like an
Yeah. And then you get all the way up here to Ogneson, right? Z equals 118. And it only has one extremely unstable isotope. 1.8 millisecond half-life, half-life. And it has alpha, its major radiation is alpha radiation. And essentially it just becomes something else right away. Right?
Where are you seeing that it's only alpha radiation is alpha?
Well, down at the very bottom it says major radiations.
Oh, okay.
It's an alpha particle radiation. So,
So
and there's no numbers for any kind of, it says decay is alpha 100%.
So the ones that have multiple, you don't know which one it will do. You just-
Yeah, but they do have percentages. So some are more common than others, essentially. More likely than others. Oh, they have, I never read instructions. That's a major fault of mine. Move the chart and drag. Use wheel to, so that's why it was zooming. Anyway, so you can move it around using this thing, I guess. It didn't work for me. Anyway, so table of the nuclides. Good stuff there. Now, in the book, there's a lot of information about things like stability. They've found a lot of patterns as they've studied this. For example, if you have a certain number of protons and a certain number of neutrons, and if they're odd or they're even or something like this, there's a lot of different patterns that tend to form stable and tend to form unstable. And they have a lot of things like that laying around in these chapters that are interesting. Also, whenever you lose energy in your nucleus, even if you lose a gamma ray, you're going to lose some mass. There's going to be a mass defect according to E equals mc squared. So even when you decay just gamma decay, and you don't lose any particles from the nucleus, you still lose mass. That energy leaves in the form of, it leaves in the form of energy, but it was being stored in the form of mass. So, so they talk about a lot of these things. They talk about particular types of decay, like beta decay in some particular instances. Lots of things going on. They calculate that mass defect again using E equals mc squared. But it's mostly just kind of details and some observations that have been made over time. So this is, of course, related to the half-life, which we talked about in the lab. So I won't go over that too much. You'll learn most of that in lab. So here they talk about carbon dating something like the Shroud of Turin. Right? When the Shroud of Turin was found, people thought It was the actual shroud of Jesus Christ. And so they did some testing on it, and they essentially calculated how much carbon-14 is left in it. Because living creatures breathe in carbon-14 from the atmosphere, but once it's in their body, it starts decaying off. So living creatures have about the same amount of carbon-14 all the time because they're always eating in new plants that have breathed in carbon dioxide from the atmosphere. But once you die, you stop eating things and you stop breathing things, and it just starts to decay off. So you can measure how much carbon-14 is left by measuring radiation in a sample of something that was made from a living creature at some time. And then you can calculate about how old it is by how much is about left. And that's what they do in this example. And they determine that it's about 690 years old, this Shroud of Turin, which of course is over 1,000 years off from Christ's death. So not likely, right? So they talk about that. You can carbon date with other things. Carbon dating only works for things that are thousands of years old because its half-life is only thousands of years. If you want to go back millions of years or hundreds of thousands of years, you might need to use something else. And there are other things out there that have different half-lives that we use for that. And I think they talk about strontium and something else, but so anyway, they talk about this in a lot of different ways. Here they talk about binding energy in particles, hydrogen and helium having these very low binding energies, these ones having very high ones. And that essentially means this stuff is more stable, this stuff is less stable. And then they go on to talk about nuclear fission, which we've already talked about. And they talk about this idea of tunneling, where particles can actually jump out of an atom just randomly without having actually to go over their energetic barrier. It's another quantum mechanic effect. But anyway, they talk about a lot of things. There's not a lot of calculation involved. There's not a lot of problem solving involved. It's mostly just here's quantum mechanics, here's particle physics, here's nuclear physics in a nutshell. I hope you enjoyed it. And now let's move on. So,
I can't really expect you to get into the nitty-gritty. It's its own thing.
no, I mean, frankly, I've never even taught quantum mechanics since I was a graduate student. I taught it as a graduate student, but since then I've taught nothing but undergraduate physics, or low-level undergraduate physics. And so if I was going to teach quantum mechanics again, I'd probably have to take a year off just to learn it again. There's so much involved. My understanding of it has waned as the years have gone by, and I've not taught it. So, but anyway, yeah. So that's kind of where we're at with that. That chapter's done with. And where are we in chapters here? We've got the medical applications, particle physics, and frontiers. So, and next week is our last week, right? So next week we'll go on our tour. We'll probably just let's see, what homeworks do we have?
32 doesn't have anything on it.
So 32 has no homework in it, but that's good because we're not covering it, right?
Yeah. 31 does.
And 31 is going to be mostly stuff. That's the wrong class. 31 is that's the wrong class. Yeah, I'm in the wrong class in both of these. That's great. Anyway, there shouldn't be anything too difficult in 31, I don't think. Still have a bunch of questions to answer here. Sorry for not getting back to your questions. I know several of you have asked questions, but I had a problem with my open math the other day and didn't fix it till yesterday. So, chapter 31 has 14 questions. Nothing in here too challenging, I don't think. And then 32, you says, has nothing. 33 has some particle stuff in it. This is not right. This is not particle physics. What is this?
It's
says wave mechanics.
Yeah, I was gonna say this last one.
Yeah, that's not any good. Let's just close that.
And done.
And what's the last one?
Alex,
Yeah, so these two are not correct. I need to just close those. So we're pretty much done with homework. How about that?
It's A-okay.
We get prep for the final.
Yeah, so if you guys want to do a final prep review, I'm totally fine with that. We just need to decide when to do it.
Is final on our own time. We're just fine. It doesn't have to necessarily follow the schedule.
Yeah, the final is whenever you want to do it.
I wonder the names.
Yeah, if either of you want any of that leftover pizza, you're welcome to. So we're all done for today. Zach, you can, what's that? I just brought it in this morning. We're done for today, Zach, so you should have your lab there. Have fun with that. And we'll see you later. Let's see. Okay. What time is it? All right. Pizza Damascus. One of my favorite.
Did you do it? That's for us. We use everybody here knows about it.
This problem, I was doing this for 15 minutes, making sure,
And like, I didn't know what I was doing. I just kind of, this is what I did. So,
This is the shower.
no, I don't know. This is a washer. Yeah, so, You're very private. Like, whenever I have my phone and stuff, you know, it's always a random thing you constantly text. You're like this.
We were just used to growing up in Simmons or those beach jump.
Necessarily hear what's going on the phone. It's always weird to get that reaction like this.
It's not bad.
Yeah. I think that the only time in my life I necessarily had to keep my phone kind of more security than I live in Atlanta. Get some 911 text from people there. And it was also, certain people that would just send things that they were working. Like that. You come from a family where you don't like your siblings.
No, I have come on.
Yeah. It's not like their business. Was it younger brothers or sisters or your house too?
Older sibling. I'm the youngest.
You're the youngest? How old is your oldest? Wow.
It doesn't seem like we have the same age, which is weird.
What do they look like older than you?
Yeah.
Yeah.
I did, yeah. Something. Yeah, I know.
Because aside from my demeanor, sometimes my voice seems low. I'm not kidding. I get really confused. Like, some people be like, is he really young? Is he really young? But I'll take this. I've done a lot of things to slow gradually my and I'm talking to you about that. I've done all sorts of research, but has it worked? I don't know. I don't have control of the hearing aids. You have to follow me. And so I have no idea. Is it working? I don't know. But every time I meet people that are my age, they always look a lot older. They look like they've been their kid or something. It's really weird. I'm curious. You tell me what the difference is when you figure it out. Do they have like
I think it's just because he has kid.
oh, yeah.
You see, he has a kid right
I'm not doing
now. I think he's a vet. He's been through 7 years of college.
It's been through 7 years in college. The only thing I've done noteworthy is travel for all that time. College is fun. I'm doing it in reverse. Normal people go to college and then have the life experience. With the life experience, now I'm going to college.
Nothing brings. He knows my kids, he knows at least three kids.
You thought about the same thing, and it's like, listen, you can't even, because of how narrow the street is, it's sort of hard to be. Yeah, I mean, I don't want to be honest with you, but at the same time, fairly obvious. Yeah. I get what you're saying, I know exactly what you're doing. I thought that too. And then this side. It's like, I made it for
Like, this is.
excited about actually doing intro physics right with the calculator. So it's usually all right. What could happen? You could have just did the, what do you call it? Alpha supplement. And that'd be like, oh, well, he must have went back on his own time, covered all this material, physics things, leading up to about one, so they cover some, maybe even some, electricity magnitude. He covered all the calculus, they learned how to write everything. You can build the equation yourself, and not just hand it down the grade, final in step without knowing. But I love giving myself a foundation for what they're going to expect of you. If you go on to university, they're going to expect you to have taken that calculator, but you've already got credit for it in your degree for going here. And they're like, oh, this must be fun. That's why I think it's good to go to the calculator version here, because at least then for sure, we're going to get that experience rather than show up at university and get credit for things. Oh, that's engineering.
Well, that's one of the
Dude, well, that's the other thing that's super cool. At least you can be on student count too. There's six though. Six. That could be anybody.
Oh, it's true.
Oh,
I like it. Most part, it's just a subject you're kind of difficult to do. I was in the, I think,
better for you.
I have one one-on-one with them.
Yeah.
That's like, didn't homework. Well, are you gonna take Calc 3 next semester? Because you're taking Calc 2. Nice. So you're taking on the chop here.
You don't have an offer.
Yeah.
Yeah, trying to get into a different progression, but it's just not in the cards if I want to stay on track. Has there been anybody you reviewed that?
All of them are actually from that criminal, so she don't know if that's another one.
Who is it?
Ms. Johnson. There's like 18 minutes in that class.
There's what?
There's like 18 minutes in that.
Oh, I got one more. Actually, yeah, I mean, I could do this. I have a pen. I have an apple. Well, that reminds me of Doritos. Really good. Under the Silvara soda machine the other day. I was like, yeah, I put in 5. I didn't know it could take 5. Just make my selection. You know, 4 quarters.
That was $4. You know there's ones in California that price is based on temperature. So in the morning at school, it's like 50 cents and they're about like in the heat of the day and noon, like 250.
That's evil. It's like, it's really hot outside. Wouldn't you like
It's
to
grinding.
We can see my wallet. Okay, so, hey, you like that? You like your, I never get over there.
That's the same cookie.
Well, so, I guess that's the local name.
Um,
I don't think I got enough for it.
how hard would it be to make a picture frame with 3D print? And is
Picture
that,
frame with
is that
3D
possible for me or is that,
Proof with that.
or like, okay,
As long as you design the model, like build it, what I would tell you is this.
it's very,
That has a side description. The way to get around that is to build something that you can connect together. If you can do something like that, you can print off all the parts, put it together like later. That can work. I think I got enough for it.
Never heard of Tinker Tech? It's a place you can design 3D objects. And it's compatible with 3D printers.
It's cold pizza.
Cold pizza.
So you don't have to heat this pizza. You have to eat it when it's cold.
No, you can put it in the microwave.
Uh,
You want to put it in the microwave?
yeah.
They have some plates in the microwave.
Oh, it has mushrooms. I don't eat mushrooms.
Don't eat mushrooms.
Yeah.
Hey, is the pepperoni back there left over from yesterday? In the fridge? Do you want it?
Or you can eat it, whatever. I'll eat whatever's left.
I got some pepperoni.
Yeah, I'm trying to.
Yeah. That's great. Valley Kings. So, what do you think on me? See,
Yeah.
the day before, and it's just kind of been collecting in the refrigerator.
Ah,
So cleaning up the refrigerator. Just three pizza. Should have brought the ice cream, we had ice cream too. So this is homemade from our house. That's pepper and olive and mushroom. This is from Little Caesars. And this one is obviously other things. Good.
what's the time now?
And we have hot sauce too in the back.
Yeah, you got it.
So
So that one is a pepperoni from the back in the refrigerator. And this is just a combination from Little Caesars. This is a combination homemade. Little Caesars, yeah. So that one's in the fridge. Yep, that one's in the fridge. You can, in the microwave for like 35 seconds is probably. All right. Oh, you know what I forgot to do? I forgot to stop my recording of class. I'm still recording.